We all use money pretty much every single day. But have you ever stopped to think about what it really is? Sure, we're taught that it's a medium of exchange, a unit of account, basically a social agreement. But what if there's something more to it? Something more fundamental, something physical that underpins its value, something governed by the laws of nature itself? Yeah, take a look at this dollar bill. We know what we can buy with it. But what does its value truly represent in the physical world? In this explainer, we're going to peel back those financial layers and look at the hardware of the economy, the real-world engine that our money is supposed to command. Mainstream economics usually treats money as software. It's just a social construct, right? A kind of neutral veil draped over the real economy. But there's a different school of thought, coming from a field called biophysical economics, that sees money as hardware, a direct claim on physical work and real resources, something that's ultimately governed by the unshakable laws of physics. So, to really understand money's hardware, we first have to shift our perspective. We need to see the economy not just as a marketplace of human choices, but for what it actually is at its core, a physical engine, a kind of metabolic system that has to consume energy just to function. And believe it or not, this isn't some brand new idea. Over a century ago, a Nobel Prize-winning chemist named Frederick Soddy argued that economics was, fundamentally flawed because it totally ignored the laws of thermodynamics. He saw that all physical activity, and that includes our entire economy, is governed by the flow of energy. And that brings us to the formal field of biophysical economics. It frames the economy as a dissipative system. Now, what on earth does that mean? Well, think of it like a living organism. It has to consume high-quality, low-entropy energy, stuff like food or fuel, and it transforms that energy into complex structures like our cities and our technology. But in the process, it inevitably produces high-entropy waste, which is just a measure of disorder like heat and pollution. Soddy was a major pioneer here. He made this crucial distinction between real wealth, physical things that rust, break, and decay, and virtual wealth, like money and debt, which don't have to obey those physical laws. And then later, the economist Nicholas Georgescu-Roegen really solidified this view, arguing that the whole economic process is permanently bound by the law of entropy, meaning every resource we use is, in the end, permanently degraded. So if the economy runs on energy, how can we actually measure its real-world efficiency? How do we know how much fuel is actually in the tank for society to use, especially after you account for the energy it takes just to get that fuel? The key metric here is something called EROI, or Energy Return on Investment. It's a simple but really profound ratio. For every 1 unit of energy we spend to find and extract a resource, how many units of energy do we get back? This simple number reveals our net energy surplus, the real energy profit that powers literally everything else in our civilization. This slide shows a really stark trend. Back in the mid-20th century, if you discovered a new oil field, you could get an incredible EROI of 80 to 1. You'd spend 1 barrel's worth of energy and get 80 barrels back. But for many of today's unconventional sources, like tar sands or shale oil, that ratio has just plummeted, sometimes as low as 5 to 1. And this points to a massive challenge. Research suggests that a complex society like ours needs a minimum EROI, maybe somewhere between 3 to 1 and 12 to 1, just to sustain all the things we take for granted, like education, healthcare, infrastructure, even the arts. As that EROI number falls, more and more of our energy has to be reinvested simply into getting more energy, and that leaves less for everything else. Which brings us right back to our original question. If the economy truly runs on this net energy, then money, at its core, must be a claim on that energy. So, is it actually possible to measure the physical value of a single dollar? This leads us to a concept called the energy value ratio, or EVR. The question it asks is simple. How much embodied energy, measured in megajoules, can $1 actually purchase? The EVR is basically an attempt to find the physical floor underneath our abstract financial system. Now, calculating this requires a really key distinction. When you buy gasoline, for example, the energy is the product. It's simple. But when you buy, say, a loaf of bread, its real energy cost isn't just its calories. The EVR is based on its embodied energy, all the energy required across the entire supply chain, from farming the wheat to baking the loaf to getting it to you. So let's look at some actual numbers for a direct energy purchase. When you buy $1 worth of gasoline, you're buying its chemical potential. That transaction gives us a baseline energy value ratio of right around 20 megajoules per dollar. Okay, but what about that loaf of bread? When you account for all the energy used in its production and delivery, a dollar's worth of bread commands an EVR of about 25 megajoules per dollar. And what's so fascinating is how close these numbers are. It suggests that underneath all the market noise, the dollar has a surprisingly consistent physical purchasing power. All right, let's take this biophysical lens and apply it to a very modern puzzle, cryptocurrency. How does a purely digital asset like Bitcoin fit into this world of physical work and embodied energy? This is a great test case. To get our heads around this, let's use a little analogy. Think of an Arctic fox. It survives by making a constant calculation. Is the energy I get from eating a mouse worth the energy I spend hunting it? Now imagine a cryptographic mouse. To catch it, the fox has to burn a massive amount of real calories. But when it finally does, it discovers the mouse has zero nutritional value. In the physical world, that fox would starve. That analogy really illustrates a key distinction we need to make: the difference between useful work and proof of work. Useful work is energy spent to power civilization, to pump water, build cars, or grow food. The energy spent on proof of work mining, on the other hand, is used pretty much exclusively to secure a digital ledger by solving incredibly hard math puzzles. From a thermodynamic perspective, this makes proof of work systems a very interesting kind of thing. You could almost call them an entropy engine. They are incredibly good at one thing: converting high-quality energy directly into security and waste heat. But notice that this process doesn't produce any intermediate physical utility for the broader economy. It completely bypasses the useful work stage. So what's the big takeaway here? What does this all mean? Well, this whole biophysical perspective really pushes us toward a different way of thinking about wealth altogether, one that's grounded in the physical reality of energy flows measured in joules, not just in dollars. And look, this isn't just an academic exercise. Thinking through this biophysical lens can help us craft much more effective energy policy. It lets us assess the true efficiency of different economies, understand the real resource footprint of the things we buy, and, crucially, it helps us distinguish between economic activities that produce real physical value and those that, well, don't. And all of this leads us to the final and most important question. In a world of finite energy and tightening energy returns, the way we define value isn't just a matter of economics anymore. It's a matter of basic sustainability. So how must we adapt our financial software to align with our planet's very real physical hardware?